Light. Introduction of light. Light is a very complex phenomenon, but in many situations, its behavior can be understood with a simple model based on rays and wave fronts. A ray is a thin beam of light that travels in a straight line. A wave front is the line or surface connecting all the light that left a source at the same time. For a source like the sun, rays radiate out in all directions. The wave fronts are spheres centered on the sun. If the source is a long way away, the wave fronts can be treated as parallel lines. Rays and wave fronts can generally be used to represent light when the light is interacting with objects that are much larger than the wavelength of light, which is about 500 nm. In particular, we'll use rays and wave fronts to analyze how light interacts with mirrors and lenses. Reflection of light. A highly polished surface such as a mirror reflects most of the light falling on it. You are already familiar with the laws of reflection of light. Let us recall these laws. 1. The angle of incidence is equal to the angle of reflection, and 2. The incident ray, the normal to the mirror at the point of incidence, and the reflected ray all lie in the same plane. These laws of reflection are applicable to all types of reflecting surfaces, including spherical surfaces. You are familiar with the formation of image by a plane mirror. What are the properties of the image? Image formed by a plane mirror is always virtual and erect. The size of the image is equal to that of the object. The image formed is as far behind the mirror as the object is in front of it. Further, the image is laterally inverted. How would the images be when the reflecting surfaces are curved? Let us explore. Take a large shining spoon. Try to view your face in its curved surface. Do you get the image? Is it smaller or larger? Move the spoon slowly away from your face. Observe the image. How does it change? Reverse the spoon and repeat the activity. How does the image look like now? Compare the characteristics of the image on the two surfaces. The curved surface of a shining spoon could be considered as a curved mirror. The most commonly used type of curved mirror is the spherical mirror. The reflecting surface of such mirrors can be considered to form a part of the surface of a sphere. Such mirrors, whose reflecting surfaces are spherical, are called spherical mirrors. We shall now study about spherical mirrors in some detail. The reflecting surface of a spherical mirror may be curved inwards or outwards. A spherical mirror whose reflecting surface is curved inwards, that is, faces towards the center of the sphere, is called a concave mirror. A spherical mirror whose reflecting surface is curved outwards is called a convex mirror. The schematic representation of these mirrors, you may note in these diagrams that the back of the mirror is shaded. You may now understand that the surface of the spoon curved inwards can be approximated to a concave mirror, and the surface of the spoon bulged outwards can be approximated to a convex mirror. The center of the reflecting surface of a spherical mirror is a point called the pole. It lies on the surface of the mirror. The pole is usually represented by the letter P. The reflecting surface of a spherical mirror forms a part of a sphere. This sphere has a center. This point is called the center of curvature of the spherical mirror. It is represented by the letter C. Please note that the center of curvature is not a part of the mirror. It lies outside its reflecting surface. The center of curvature of a concave mirror lies in front of it. However, it lies behind the mirror in case of a convex mirror. The radius of the sphere of which the reflecting surface of a spherical mirror forms a part is called the radius of curvature of the mirror. It is represented by the letter R. You may note that the distance PC is equal to the radius of curvature. Imagine a straight line passing through the pole and the center of curvature of a spherical mirror. This line is called the principal axis. Remember that principal axis is normal to the mirror at its pole. Let us understand an important term related to mirrors through an activity. Caution! Do not look at the sun directly or even into a mirror reflecting sunlight. It may damage your eyes. Hold a concave mirror in your hand and direct its reflecting surface towards the sun. Direct the light reflected by the mirror onto a sheet of paper held close to the mirror. Move the sheet of paper back and forth gradually until you find on the paper sheet a bright, sharp spot of light. Hold the mirror and the paper in the same position for a few minutes. What do you observe? Why? The paper at first begins to burn, producing smoke. Eventually, it may even catch fire. Why does it burn? The light from the sun is converged at a point as a sharp, bright spot by the mirror. In fact, this spot of light is the image of the sun on the sheet of paper. This point is the focus of the concave mirror. The heat produced due to this image from the position of the mirror gives the approximate value of focal length of the mirror. Let us try to understand this observation with the help of a ray diagram. Observe closely. A number of rays parallel to the principal axis are falling on a concave mirror. Observe the reflected rays. They are all meeting or intersecting at a point on the principal axis of the mirror. This point is called the principal, the focus of the concave mirror. How are the rays parallel to the principal axis reflected by a convex mirror? The reflected rays appear to come from a point on the convex mirror. The principal focus is represented by the letter F. The distance between the pole and the principal focus of a spherical mirror is called the focal length. It is represented by the letter F. The reflecting surface of a spherical mirror is by and large spherical. The surface, then, has a circular outline. The diameter of the reflecting surface of a spherical mirror is called its aperture. Distance mn represents the aperture. We shall consider in our discussion only such spherical mirrors whose aperture is much smaller than its radius of curvature. Is there a relationship between the radius of curvature r and focal length f of a spherical mirror? For spherical mirrors of small apertures, the radius of curvature is found to be equal to twice the focal length. We put this as r is equal to 2f. This implies that the principal focus of a spherical mirror lies midway between the pole and center of curvature. Maybe you've gone into a mirror fun house that has all these weird mirrors that make you look 10 feet tall, skinny in the middle, and wide at the top. Obviously, these are not regular plain mirrors. Instead, they are all curved and bumpy and misshaped. Don't worry, we are not going to be analyzing mirrors that are that weird, but we will be looking at curved mirrors. Imagine taking a giant ball and cutting a section out of it. You spray some shiny paint on the inside and outside and you have a curved mirror. The first kind we will be looking at is a concave mirror, which would mean that you made the inside of the ball shiny. Then we will look at convex mirrors, where the outside of the ball was made shiny. Concave mirrors. To be able to figure out how an image will be formed in one of these concave mirrors, you need to be aware of a few basic parts. Check out Figure 1 and the description of each part that follows. Center C. The center shown in the diagram is where the center of the sphere would be. In the diagram I have drawn, I've had to exaggerate the shape of the mirror a bit to be able to use it in some of the diagrams later on. But you should be able to get the basic idea. Like a regular circle, the distance from the center to the surface of the mirror is the radius. Focus or focal point, F. If an object was infinitely far away from the mirror, the light from it would converge on this one point. In the diagrams we are doing, we will mostly be looking at how some light rays pass through this focal point. The focal point is exactly in between the mirror and the center. Since the distance between the center and the mirror is the radius, the distance from the focal point to the mirror is half of the radius. Principal axis. The blue line is the principal axis, a line that we will use as a reference point in our diagrams. It passes through the center and is perpendicular to the surface of the mirror. There are 3 rules you need to use to figure out where the image of the object will appear. You only need to use 2 to actually locate the image, but you can use the 3rd as a check. All of the rules involve what a ray will do when it leaves the object. You will need to have a ruler to draw the lines when you figure out these problems. When you sketch the curved mirror itself, you'll find you don't have to be too careful about making its shape perfect. Close enough will give you decent results. The object we will be using in these examples is an arrow pointing up. That way, we will have an easy time seeing if the image is inverted or not. The image will appear where any 2 reflected rays cross. Rule number 1. Any ray through the focal point will reflect parallel to the principal axis. Don't start worrying about how that ray of light came off the object and went straight through the focus. It just did. Light reflects off objects at all sorts of angles, and if it will help us to find where an image is, we might as well assume one ray goes right through the focus. Rule number 2. Any ray parallel to the principal axis will reflect so that it passes through the focal point. I know this sounds exactly the same as the first rule, but look at it carefully and you'll see that it is the opposite. Notice the spot where I marked the red ray crossing the black ray from Rule 1. This shows me where the image will appear. Since all my rays were drawn from the tip of the object, this shows where the tip of the image will be. I know that since the base of the object is on the principal axis, it will appear there in the image also. Figure 4. We draw the image as a solid line because the rays of light that make the image are actually traveling through that point. If I was to hold a piece of paper right there, I would see the image appear there. It is a real image. Also notice that the image is upside down or inverted and slightly smaller than the original. This is not always the case with concave mirrors. You might even find that your rays need to be extended to behind the mirror to be able to cross each other. Then the image would be a virtual image behind the mirror. For any image, you will need to classify it as 1. Real or virtual, 2. Erect or inverted, 3. Smaller, bigger, or same size. Although we know where the image is and that it is a real, inverted, smaller image, we can still confirm it using our last method. Rule number 3. Any ray that passes through the center will reflect back through the center. Unfortunately, this is the least reliable way to draw a ray, since small errors in the quick sketches we draw will become big errors. I had to assume that if the mirror was big enough, it would have bounced back somewhere around there. Notice that it hits just about where the other two rays meet up. We are probably doing okay. Always keep in mind that you will usually only use 2 of these 3 rules. Try to use the first 2 whenever possible. Only use the third rule if you have to. Convex mirrors. The same set of rules shown above apply to convex mirrors. It's just that things will look a bit different since convex mirrors have their focal point and center behind the mirror. Convex mirrors also typically make a small virtual image of the original object. Let's look at an example using the 3 rules covered above for concave mirrors. The only difference is that I will extend the rays behind the mirror as dotted lines to be able to show how they pass through the focal point or through the center. Use rule number 2 to draw the ray coming off of the top of the object parallel to the principal axis. When it hits the mirror, it bounces off so that a dotted line drawn behind the mirror will pass through the focal point. Rule number 3. This ray comes off the top of the object, aiming straight for the center. Where it hits the mirror, it will bounce back, but I draw a dotted line behind the mirror to show where the ray would have gone. Notice that there is now a place where the 2 dotted lines hit. This is where the image will appear. The image is virtual. It is erect and shrunken down a bit. The formulas. There are a couple of formulas you can use to figure out where an image will appear, if it will be inverted or erect and magnified or shrunk. The first is called the mirror formula. 1 by f is equal to 1 by do plus 1 by di, where f is equal to focal length in meters, do is equal to distance from mirror to object in meters, di is equal to distance from mirror to image in meters. Ultra special notes for using the mirror formula. 1. Concave mirrors have positive focal length and convex mirrors have a negative focal length. Distances are positive if they are in front of the mirror and negative if they are behind. All measurements are made along the principal axis from the surface of the mirror. The magnification formula is m is equal to hi by ho is equal to minus di by do. Same as above plus hi is equal to height of the image in meters, ho is equal to height of the object in meters, m is equal to magnification. Ultra special notes for using the magnification formula. As above plus 1. Positive heights are above the principal axis and negative heights are below the principal axis. Positive magnifications are above the principal axis and negative magnifications are below the principal axis. Magnifications greater than 1 are bigger than the original object. Magnifications less than 1 are smaller than the original object. Example 1. A convex mirror has a radius of 20 centimeters. An object is placed 30 centimeters in front of the mirror. Determine where the image will appear. Since the radius is 20 centimeters and since the focal point is halfway in between and negative for a convex mirror, f is equal to minus 10 centimeters. 1 by f is equal to 1 by do plus 1 by di. 1 by di is equal to 1 by f minus 1 by do. 1 by di is equal to 1 by minus 10 minus 1 by 30. di is equal to minus 7.5 centimeters. Since di is negative, it appears behind the mirror as a virtual image. Image formation by a concave mirror for different positions of the object. Object is kept at infinity. Image formed at the focus F. Size of the image is highly diminished, point-sized. Nature of the image, real and inverted. Object is kept beyond C. Image formed between F and C. Size of the image diminished. Nature of the image real and inverted. Object is kept at C. Image formed at C. Size of the image same size. Nature of the image real and inverted. Object is kept between C and F. Image formed beyond C. Size of the image enlarged. Nature of the image real and inverted. Object is kept at F. Image formed at infinity. Size of the image is highly enlarged. Nature of the image real and inverted. Object is kept between P and F. Image formed behind the mirror. Size of the image enlarged. Nature of the image virtual and erect. Representation of images formed by spherical mirrors using ray diagrams. The intersection of at least two reflected rays give the position of image of the point object. Any two of the following rays can be considered for locating the image. A ray parallel to the principal axis after reflection will pass through the principal focus in case of a concave mirror or appear to diverge from the principal focus in case of a convex mirror. A ray passing through the principal focus of a concave mirror or a ray which is directed towards the principal focus of a convex mirror after reflection will emerge parallel to the principal axis. A ray passing through the center of curvature of a concave mirror or directed in the direction of the center of curvature of a convex mirror after reflection is reflected back along the same path. A ray incident obliquely to the principal axis towards a point P on the concave mirror or a convex mirror is reflected obliquely. The incident and reflected rays follow the laws of reflection at the point of incidence, making equal angles with the principal axis. Remember that in all the above cases, the laws of reflection are followed. At the point of incidence, the incident ray is such a way that the angle of reflection equals the angle of incidence. Uses of concave mirrors. Concave mirrors are commonly used in torches, searchlights, and vehicles' headlights to get powerful parallel beams of light. They are often used as shaving mirrors to see a larger of the face. The dentists use concave mirrors to see large images of the teeth of patients. Large concave mirrors are used to concentrate sunlight to produce heat in solar furnaces. Image formation by a convex mirror. We studied the image formation by a concave mirror. Now we shall study the formation of image by a convex mirror. Activity. Take a convex mirror. Hold it in one hand. Hold a pencil in the upright position in the other hand. Observe the image of the pencil in the mirror. Is the image erect or inverted? Is it diminished? Move the pencil away from the mirror slowly. Does the image become smaller or larger? Repeat this activity carefully. State whether the image will move closer to or farther away from the focus as the object is moved away from the mirror. We consider two positions of the object for studying the image formed by a convex mirror. First is when the object is at infinity, and the second position is when the object is at a finite distance from the mirror. The ray diagrams for the formation of image by a convex mirror for these two positions of the object, the results are summarized as given below. Position of the object. At infinity, position of the image. At the focus F behind the mirror. Size of the image. Highly diminished point sized. Nature of the image. Virtual and erect. Position of the object. Between infinity and the pole P of the mirror. Position of the image. Between P and F behind the mirror. Size of the image. Diminished. Nature of the image. Virtual and erect. Use of convex mirrors. Convex mirrors are commonly used as rear view or wing mirrors in vehicles. These mirrors are fitted on the sides of the vehicle, enabling the driver to see traffic behind him or her to facilitate safe driving. Convex mirrors are preferred because they always give an erect, though diminished image. Also, they have a wider field of view as they are curved outwards. Thus, convex mirrors enable the driver to view much larger area than would be possible with a plain mirror. Sign convention for reflection by spherical mirrors. While dealing with the reflection of light by spherical mirrors, we shall follow a set of sign conventions called the new Cartesian sign convention. In this convention, the pole P of the mirror is taken as the origin. The principal axis of the mirror is taken as the x-axis of the coordinate system. The conventions are as follows. The object is always placed to the left of the mirror. This implies that the light from the object falls on the mirror from the left-hand side. All distances parallel to the principal axis are measured from the pole of the mirror. All the distances measured to the right of the origin are taken as positive, while those measured to the left of the origin are taken as negative. Distances measured perpendicular to and above the principal axis are taken as positive. Distances measured perpendicular to and below the principal axis are taken as negative. These sign conventions are applied to obtain the mirror formula and solve related numerical problems. Mirror formula and magnification. In a spherical mirror, the distance of the object from its pole is called the object distance, or U. The distance of the image from the pole of the mirror is called the image distance, or V. You already know that the distance of the principal focus from the pole is called the focal length, F. There is a relationship between these quantities given by the mirror formula, which is expressed as 1 by V plus 1 by U is equal to 1 by F. This formula is valid in all situations for all spherical mirrors for all positions of the object. You must use the new Cartesian sign convention while substituting numerical values for U, V, F, and R in the mirror formula for solving problems. Magnification. Magnification produced by a spherical mirror gives the relative extent to which the image of an object is magnified with respect to the object size. It is expressed as the ratio of the height of the image to the length of the object. It is usually represented by the letter m. If h is the height of the object and h dash is the height of the image, then the magnification m produced by a spherical mirror is given by m is equal to height of the image by height of the object. M is equal to h dash by h. The magnification m is also related to the object distance u and the image distance v. It can be expressed as magnification m is equal to h dash divided by h is equal to minus v by u. You may note that the height of the object is taken to be positive as the object is usually placed above the principal axis. The height of the image should be taken as positive for virtual images. However, it is to be taken as negative for real images. A negative sign in the value of the magnification indicates that the image is virtual. Refraction of light. Light seems to travel along straight line paths in a transparent medium. What happens when light enters from one transparent medium to another? Does it still move along a straight line path or change its direction? We shall recall some of our day-to-day experiences. You might have observed that the bottom of a tank or a pond containing water appears to be raised. Similarly, when a thick glass slab is placed over some printed matter, the letters appear raised when viewed through the glass slab. Have you seen a pencil partly immersed in water in a glass tumbler? It appears to be displaced at the interference of air and water. You might have observed that a lemon kept in water in a glass tumbler appears to be bigger than its actual size when viewed from the sides. Let us consider the case of the apparent displacement of a pencil partly immersed in water. The light reaching you from the portion of the pencil inside water seems to come from a different direction compared to the part above water. This makes the pencil appear to be displaced at the interface. For similar reasons, the letters appear to be raised when seen through a glass slab placed over it. Does a pencil appear to be displaced to the same extent if instead of water we use liquids like kerosene or turpentine? Will the letters appear to rise to the same height if we replace a glass slab with a transparent plastic slab? You will find that the extent of the effect is different for a different pair of media. These observations indicate that light does not travel in the same direction in all media. It appears that when traveling obliquely from one medium to another, the direction of propagation of light in the second medium changes. This phenomenon is known as refraction of light. Let us understand this phenomenon further by doing a few activities. Activity: place a coin at the bottom of a bucket filled with water. With your eye to a side above water, try to pick up the coin in one go. Did you succeed in picking up the coin? Repeat the activity. Why did you not succeed in doing it in one go? Ask your friends to do this. Compare your experience with theirs. Refraction through a rectangular glass slab. To understand the phenomenon of refraction of light through a glass slab, activity: fix a sheet of white paper on a drawing board using drawing pins. Place a rectangular glass slab over the sheet in the middle. Draw the outline of the slab with a pencil. Let us name the outline as A, B, C, D. Take 4 identical pins. Fix 2 pins, say E and F, vertically such that the line joining the pins is inclined to the edge AB. Look for the images of the pins E and F through the opposite edge. Fix 2 other pins, say G and H, such that these pins and the images of E and F lie on a straight line. Join the positions of tip of the pins E and F and produce the line up to AB. Let EF meet AB at O. Similarly, join the positions of tip of the pins G and H and produce it up to the edge CD. Let HG meet CD at O'. Join O and O'. Also produce EF up to P, as shown by a dotted line. In the activity, the light ray has changed its direction at points O and O'. Note that both the points O and O' lie on surfaces separating 2 transparent media. Draw a perpendicular NN' to AB at O and another perpendicular MM' to CD at O'. The light ray at point O has entered from a rarer medium to a denser medium, that is, from air to glass. Note that light ray has bent towards the normal. At O', the light ray has entered from glass to air, that is, from a denser medium to a rarer medium. The light here has bent away from the normal. Compare the angle of incidence with the angle of refraction at both refracting surfaces AB and CD. EO is the incident ray. OO' is the refracted ray. O'(H) is the emergent ray. The emergent ray is parallel to the direction of the incident ray. The extent of bending of the ray of light at the opposite parallel faces A, B and CD of the rectangular glass slab is equal and opposite. That is why the ray emerges parallel to the incident ray. However, the light ray is shifted sideward slightly, called the lateral displacement. You are familiar with the refraction of light. Refraction is due to change in the speed of light as it enters from one transparent medium to another. Experiments show that refraction of light occurs according to certain laws. The following are the laws of refraction of light. 1. The incident ray, the refracted ray, and the normal to the interface of 2 transparent media at the point of incidence all lie in the same plane. 2. The ratio of the sine of angle of incidence to the sine of angle of refraction is a constant for the light of a given color and for the given pair of media. This law is also known as Snell's law of refraction. If I is the angle of incidence and R is the angle of refraction, then sin I divided by sin R is equal to constant. This constant value is called the refractive index of the second medium with respect to the first. Let us study about refractive index in some detail. The refractive index. You have already studied that a ray of light that travels obliquely from one transparent medium into another will change its direction in the second medium. The extent of the change in direction that takes place in a given pair of media is expressed in terms of the refractive index, the constant. The refractive index can be linked to an important physical quantity, the relative speed of propagation of light in different media. It turns out that light propagates with different speeds in different media. Light travels the fastest in vacuum with the highest speed of 3 × 10⁸ meters per second. In air, the speed of light is only marginally less compared to that in vacuum. It reduces considerably in glass or water. The value of the refractive index for a given pair of media depends upon the speed of light in the two media as given below. Consider a ray of light traveling from medium 1 into medium 2. Let V1 be the speed of light in medium 1 and V2 be the speed of light in medium 2. The refractive index of medium 2 with respect to medium 1 is given by the ratio of the speed of light in medium 1 and the speed of light in medium 2. This is usually represented by the symbol N21. This can be expressed in an equation form as N21 is equal to speed of light in medium 1 divided by speed of light in medium 2, which is equal to V1 by V2. By the same argument, the refractive index of medium 1 with respect to medium 2 is represented as N12. It is given by N21 is equal to speed of light in medium 2 divided by speed of light in medium 1, which is equal to V2 by V1. If medium 1 is vacuum or air, then the refractive index of medium 2 is considered with respect to vacuum. This is called the absolute refractive index of the medium. It is simply represented as N2. If c is the speed of light in air and v is the speed of light in the medium, then the refractive index of the medium Nm is given by Nm is equal to speed of light in air divided by speed of light in the medium, which is equal to c by v. The absolute refractive index of a medium is simply called its refractive index. The refractive index of several media is given in the table. From the table, you can know that the refractive index of water Nw is equal to 1.33. This means that the ratio of the speed of light in air and the speed of light in water is equal to 1.33. Similarly, the refractive index of crown glass Ng is equal to 1.52. Such data are helpful in many places. However, you need not memorize the data. Absolute refractive index of some material media. Material medium refractive index. Air 1.0003. Ice 1.31. Water 1.33. Alcohol 1.36. Kerosene 1.44, fused quartz 1.46, turpentine oil 1.47, benzene 1.50, crown glass 1.52, Canada balsam 1.53, rock salt 1.54, carbon disulfide 1.63, dense flint glass 1.65, ruby 1.71, sapphire 1.77, diamond 2.42. Note from the above table that an optically denser medium may not possess greater mass density. For example, kerosene having higher refractive index is optically denser than water, although its mass density is less than water. The ability of a medium to refract light is also expressed in terms of its optical density. Optical density is not the same as mass density. We have been using the terms rarer medium and denser medium. It actually means optically rarer medium and optically denser medium. The medium with a larger refractive index is the optically denser medium, and the medium with a lower refractive index is optically rarer. The speed of light is higher in a rarer medium than a denser medium. Thus, a ray of light traveling from a rarer medium to a denser medium slows down and bends towards the normal. When it travels from a denser medium to a rarer medium, it speeds up and bends away from the normal. The refraction by spherical lenses. A transparent material bound by two surfaces, of which one or both surfaces are spherical, forms a lens. This means that a lens is bound by at least one spherical surface. In such lenses, the other surface would be plane. A lens may have two spherical surfaces bulging outwards. Such a lens is called a double convex lens. It is simply called a convex lens. It is thicker at the middle as compared to the edges. Convex lens converges light rays. Hence, convex lenses are called converging lenses. Similarly, a double concave lens is bounded by two spherical surfaces curved inwards. It is thicker at the edge than at the middle. Such lenses diverge light rays. Such lenses are called diverging lenses. A double concave lens is simply called a concave lens. A lens, either a convex lens or a concave lens, has two spherical surfaces. Each of these surfaces forms a part of a sphere. The centers of these spheres are called centers of curvature of the lens. The center of curvature of a lens is usually represented by the letter C. Since there are two centers of curvature, we may represent them as C1 and C2. An imaginary straight line passing through the two centers of curvature of a lens is called its principal axis. The central point of a lens is its optical center. It is usually represented by the letter O. A ray of light through the optical center of a lens passes without suffering any deviation. The effective diameter of the circular outline of a spherical lens is called its aperture. We shall confine our discussion in this chapter to such lenses whose aperture is much less than its radius of curvature. Such lenses are called thin lenses with small apertures. What happens when parallel rays of light are incident on a lens? Let us do an activity to understand this. Caution! Do not look at the sun directly or through a lens while doing this activity, or otherwise you may damage your eyes if you do so. Hold a convex lens in your hand. Direct it towards the sun. Focus the light from the sun on a sheet of paper. Obtain a sharp, bright image of the sun. Hold the paper and the lens in the same position for a while. Keep observing the paper. What happened? The paper begins to burn, producing smoke. It may even catch fire after a while. Why does this happen? The light from the sun constitutes parallel rays of light. These rays were converged by the lens at the sharp bright spot formed on the paper. In fact, the bright spot you got on the paper is a real image of the sun. The concentration of the sunlight at a point generated heat. This caused the paper to burn. Several rays of light parallel to the principal axis are falling on a convex lens. These rays, after refraction from the lens, are converging to a point on the principal axis. This point on the principal axis is called the principal focus of the lens. Let us see now the action of a concave lens. several rays of light parallel to the principal axis are falling on a concave lens. These rays, after refraction from the lens, are appearing to diverge from a point on the principal axis. This point on the principal axis is called the principal focus of the concave lens. Nature, position and relative size of the image formed by a convex lens for various positions of the object. Positions of the object at infinity, position of the image at focus f2, relative size of the image, highly diminished point sized, nature of the image, real and inverted, positions of the object beyond 2f1, position of the image between f2 and 2f2, relative size of the image, diminished, nature of the image, real and inverted, positions of the object at 2f1, position of the image at 2f2, relative size of the image, same size, nature of the image, real and inverted, positions of the object between f1 and 2f1, position of the image beyond 2f2, relative size of the image, enlarged, nature of the image, real and inverted, positions of the object at focus f1, position of the image at infinity, relative size of the image, infinitely large or highly enlarged, nature of the image, real and inverted, positions of the object between focus f1 and optical center O, position of the image on the same side of the lens as the object, relative size of the image, enlarged, nature of the image, virtual and erect. Object is kept at infinity. Image is formed at focus f1. Size of the image highly diminished, point sized. Nature of the image virtual and erect. Object is kept between infinity and optical center O of the lens. Image is formed between focus f1 and optical center O. Size of the image diminished. Nature of the image virtual and erect. A concave lens will always give a virtual, erect and diminished image irrespective of the positions of the object. Image formation in lenses using ray diagram. We can represent image formation by lenses using ray diagrams. Ray diagrams will also help us to study the nature, position and relative size of the image formed by lenses. For drawing ray diagrams in lenses, alike of spherical mirrors, we consider any two of the following rays. A ray of light from the object parallel to the principal axis after refraction from a convex lens passes through the principal focus on the other side of the lens. In case of a concave lens, the ray appears to diverge from the principal focus located on the same side of the lens. A ray of light passing through a principal focus after refraction from a convex lens will emerge parallel to the principal axis. A ray of light appearing to meet at the principal focus of a concave lens after refraction will emerge parallel to the principal axis. A ray of light passing through the optical center of a lens will emerge without any deviation in concave and convex lenses. Lens formula and magnification. As we have a formula for spherical mirrors, we also have a formula for spherical lenses. This formula gives the relationship between object distance u and image distance v and the focal length f. The lens formula is expressed as 1 by v minus 1 by u is equal to 1 by f. The lens formula given above is general and is valid in all situations for any spherical lens. Take proper care of the signs of different quantities while putting numerical values for solving problems relating to lenses. Magnification. The magnification produced by a lens similar to that for spherical mirrors is defined as the ratio of the height of the image and the height of the object. It is represented by the letter m. If h is the height of the object and h dash is the height of the image given by a lens, then the magnification produced by the lens is given by m is equal to height of the image divided by height of the object, which is equal to h dash by h. Magnification produced by a lens is also related to the object distance u and the image distance v. This relationship is given by magnification m is equal to h dash divided by h, which is equal to v divided by u.
Power of a lens. The ability of a lens to converge or diverge light rays depends on its focal length. For example, a convex lens of short focal length bends the light rays through large angles by focusing them closer to the optical center. Similarly, concave lens of very short focal length causes higher divergence than the one with longer focal length. The degree of convergence or divergence of light rays achieved by a lens is expressed in terms of its power. The power of a lens is defined as the reciprocal of its focal length. It is represented by the letter P. The power P of a lens of focal length f is given by P is equal to 1 by f.